20 meters beneath the mortal world lies the Paris Catacombs. Here, in the crypt of the Passion, this column of bones helps to stop the roof from caving in. With regular building material becoming harder to source and more expensive, could bone be the next big thing for the construction industry? In the late 1700s, Paris's graveyards were overflowing, often into neighbouring basements. For 2 years, Parisian authorities moved skeletons of the dead into old abandoned quarries, so that today the remains of over 6 million people line these tunnels. There are two forces to consider when selecting an engineering material: tension and compression. Let's leave the dead to rest and head back above ground to see how these work. This is the Eiffel Tower and a key example of our first force, tension. If you don't fancy climbing the 674 steps to the top of the tower, then you're going to have to take the elevator. The passenger cabin is placed on top of a platform, which is attached to a series of cables. Tension in these cables pulls the elevator up through the legs of the tower. Tension force stretches the cables, making them longer. By measuring how much stretching occurs, we can get a good gauge on whether the cable is about to break or not. Welcome back to the Leeds laboratory. This Tinnis-Olser machine is what we use to measure material stretch, more formally known as strain. Strain is calculated by dividing the change in length over the original length. Let's try it out using this steel rod. We begin by placing it between these two grips. The machine is now going to pull these grips apart, applying tension to the steel in the middle. As we add more and more of this tension, the steel begins to stretch. Originally 64 millimeters long, the sample has now stretched to a length of 66 millimeters. This extra 2 millimeters over the original 64 millimeter length gives us a strain value of just over 3%. At the moment, our rod has only undergone elastic deformation. This means that when we remove it from the machine, it reverts back to its original length. As you can see, by comparing it with an unstretched sample, it is impossible to tell which is which by just looking at which rod is longer. If we add in enough tension, then this stretch stays put. It's undergone something called plastic deformation. As you can see by comparing it to an unstretched sample, it's become much longer. You don't really want this for things like elevator cables, but take note. If you did this with the bones in your leg, then you would actually get taller. Before you go running off to find your nearest Tinnis-Olser machine to add a few extra centimeters of height, be careful of what happens at the next stage, when we add in even more tension. These massive Gothic towers make up the iconic western facade of the Notre Cathedral. Each of these towers weigh in at over 9,000 tons, putting the limestone base under a huge amount of compressive force. Compression is the force that pushes on an object, squeezing it together. To help understand stress, we're going to use this instrument machine. Just like the Tinnis-Olser machine from earlier, we put the sample between these two plates. Unlike the machine from earlier, these plates are now going to push the sample together. It's obvious that a thicker rod will be able to support more force than a thinner one, but that doesn't tell us anything about the material itself. A much better thing to use is stress. In order to put all samples on the same playing field, we take the force and divide it by the sample area. The Notre Dame Tower exerts 19 million newtons of force onto an area of 250 meters squared. This gives a stress of 600 kilopascals. Let's see how the steel rod fares. As we add more and more force, it goes through some very similar regions as our tension tests from earlier. First, elastic deformation, where the rod will go back to its original shape. Then crumpling, essentially equivalent to plastic deformation. And finally, failure. Since tension and compression are both measured using stress and strain, we can plot them all on the same graph. This is what's known as a StressStrain curve. Here is the tension bit of the curve. You can see the key regions. Here we have linear, elastic deformation. Next, we have the curvy plastic. And finally, this endpoint is where failure occurs. We have some very similar structures for the compression section. we've got our elastic deformation, barreling, and finally breakage. Since, as we recall, stress is measured in force per unit area and strain is percentage change in length, we can use these graphs for wildly different projects, which is useful because that's what we're doing next. Today we'll be testing the properties of steel, concrete, and bone. Steel and concrete are widely used in the construction industry. If we are to truly build with bone, it's got to be able to compete with materials that are actually being used. Unfortunately, no one I talked to was going to let me borrow an actual human bone in order to do the experiments. But this cow knuckle bone is going to do just fine. We know the theory, let's do some tests. We now have our stress-strain curve from each of the tests. Performing the best is steel. It has excellent tensile strength and very good compressive strength. Surprisingly, concrete didn't fare too well. It's pretty bad on tension and only slightly better in compression. Finally, we have bone. It did well in the tension tests as well as compression. Converting our results into more familiar units, in compression, our bone could support 3.5 tons weight. That's the equivalent to almost 4 small cars. That's pretty amazing. Can we build with bone? Yes. Should we though? Perhaps not. However, it is interesting to note that a group of researchers, by copying the internal structure of bone, were able to create a steel that was lighter, stronger, and more resistant to wear than the regular variety. We may be building with bone sooner than you might have thought. Happy Halloween, and a huge thank you to everyone who helped make this video possible, and in particular to Bob, Diane and Tony for letting us use the lab. We're producing new episodes of Engineering Europe every 2 weeks. Next episode, we're off to Austria. Until then, this has been James Dingley from the Atomic Frontier. Keep looking up.